the double angle formulas. So, sine 2 theta, how do we create the formulas? Well, using our compound angle formulas. We rewrite 2 theta as theta plus theta. And so then we can go sine, cos, cos, sine. If it's a sine, it's a sine. But we notice, oh look, sine theta, cos theta, well that's the same as cos theta, sine theta. So we end up with the first of our double angle formulas, 2 sine theta, cos theta. Cos is a little bit more interesting. You get cos theta plus theta, so we get cos, cos minus sine, sine. So that's cos squared minus sine squared. But we could rewrite that because I could say, well, look, I want it all in terms of coses. So sine squared I could change to 1 minus cos squared. Then tidying that one up, I get 2 cos squared theta minus 1. However, if I want it all in terms of sine squared, I could change the cos squared to 1 minus sine squared, and we get 1 minus 2 sine squared. So we actually have 3 different ones we could use for cos 2 theta, and I guess it just depends on the problem as to which particular one you would go and use. So cos squared minus sine squared, 2 cos squared minus 1, 1 minus 2 sine squared. They're very similar. How do we remember which one's which? Which one's the 2 minus, which one's the 1 minus 2? Again, it comes back to the first one. Cos squared's positive, sine squared's negative. So therefore, if you're using the cos squared, it's 2 cos squared minus 1. It's got to be positive. If you're using the sine squared, well then it's 1 minus 2 sine squared because the sine squared is negative in the original one. Anyway, that's how I remember it. But again, that's just how my strange mind works. Let's do the tan one. Tan theta plus theta, tan plus tan, or 1 minus tan tan. So on the top of the fraction, we end up with 2 tan theta, and on the bottom, 1 minus tan squared theta. Okay, so sine 2 theta, 2 sine theta cos theta. Cos 2 theta, cos squared minus sine squared, or 2 cos squared minus 1. But what I was saying before was where it comes in handy is we can actually rearrange this and get an expression for cos squared in terms of a double angle. So cos squared theta is a half of 1 plus cos 2 theta. Now this will come in very handy next year, I suppose, when we're doing some integration of trig. It allows us to integrate cos squared. And similarly, sine squared, because 1 minus 2 sine squared, I can make sine squared the subject. And I get a half of 1 minus. Again, you'll notice they're very similar. Again, it comes down to the sign, but cos squared, it's the positive one. Sine squared, it's the negative one. So you get 1 minus cos 2 theta there. And there's our third one, 2 tan theta or 1 minus tan squared theta. All right, let's have a look at some examples. We're told cos theta is 2/3. We want to find tan 2 theta. So I draw myself a triangle, bit of Pythagoras. Okay, I know the other side's root 5. So tan 2 theta, let's sub in. There we go, 2 lots of root 5 on 2 and 1 minus root 5 on 2 squared, tidying all that up. Eventually, we get minus 4 root 5. What does that tell you about theta? What we've probably got here, theta is probably in between 45 and 90. So that when we double it, we get an obtuse angle because the tan's negative. So we know theta can't be between 0 and 45. Because if we doubled an angle between 0 and 45, we'd still have an acute angle, and so the tan 2 theta would be positive. So, I mean, I guess we could go to our calculator and work out what it is exactly. But that's one piece of information we could gain from that. In all likelihood, theta is in between 45 and 90. Let's find the exact value. How do we do it? Well, it's in the form sine cos. Now, I've got a double angle formula that's also in the form sine cos. I'll make it a little bit more obvious by multiplying by 2 and dividing by 2. Inside the parentheses, I've now got 2 sine theta cos theta sine 2 theta. So we've got sine of 2 lots of 5 pi and 12, which is 10 pi and 12, which is 5 pi and 6, one of our exact values. Now, I don't know what you're like with radians, but I've been working with them for a lot of years now. But even to this day, when I see 5 pi and 6, I have to have a think about what that is in degrees to work out the exact value. 5 pi on 6, 150. So we're in our second quadrant. Sine's positive. The acute angle is 30 degrees. So it's a half, yeah. Half times a half, a quarter. Cos theta is 2/3. Find the exact value of sine theta on 2. This is why we call them double angle formulas and not 2 theta formulas. Because we're not restricted to have a situation where we've got theta and 2 theta. I could have a situation where I've got theta and a half theta. Because theta is double theta on 2. So I could still use the double angle formulas for this one. And here it is, where we rearrange to make sine squared the subject. This could come in useful now. Sine squared theta is a half of 1 minus cos 2 theta. But instead of going theta and 2 theta, I'm going to say it's half theta and theta. So I can find sine squared theta on 2, which then will allow me to find sine theta on 2. Cos theta, they told me, is 2/3. So sine squared is 1 on 6. Two possibilities there, plus or minus 1 on root 6. So again, without more information, I don't know whether it's positive or negative. I guess it just depends where theta lies in the quadrants as to what theta on 2 would be. So I'd need more information to go further than that. So at this stage, best we can say, plus or minus 1 on root 6. All right, let's do a trig identity question. We're going to prove this one. Square root of 1 minus cos 2x on square root of 1 plus 2x. Now, cos 2x, I've got the choice of 3 different things I can substitute in. But if I look at to what I'm going to end up with, I want to get tan x. So it would be smart to use a particular one on the top and a particular one on the bottom. Which way around should I go? Yeah, because sine on cos is tan. So if on the top one, I use 1 minus 2 sine squared, but on the bottom one, I use 2 cos squared minus 1. I guess another thing to highlight here is, if they're saying prove this is equal to this, again, it's a proof. To go straight from there to there, could you be accused of fudging it? You know what I mean? Like, because you know the final answer is going to be tan x. They've told you that. So maybe that putting in the 1 minus 2 sine squared is a good idea. So they can say, yeah, I know where I got this from. This is what I use. You know? All right. Sine squared and cos squared is, of course, tan squared, square root of tan squared, tan x. Let's have a look at one from an HSC. Wow, 20 years ago. But it's a nice question because some people wasted a lot of time in this question. Now, I don't know what you're thinking about here, how to attack this problem. But a lot of people went, sine 3 theta. Well, I could rewrite sine 3 theta as sine 2 theta plus theta. Then expand that out. And then I've got a sine 2 theta formula, expand that out and total it up. It's a lot quicker to treat it like an algebraic fraction. Because watch what happens. Right? Bottom of the fraction, well, that's just sine theta, cos theta. But look at the top. Sine, cos, cos, sine. So it's in the form sine, cos, cos, sine. If it's the sine, it's the sine. So the top is 3 theta minus theta. It's just sine 2 theta. Over, well, look what's on the bottom. By the way, I cleverly multiplied top and bottom by 2, if you didn't notice that. Okay, so now my sine 2 thetas, they're going to cancel. And I get the answer 2 that we're looking for. Let's have a look. We'll go even further back in time. Let's have a look at this one. 2 tan on 1 plus tan squared. It's very tempting to look at that and go, oh, look, left-hand side's just tan 2a, but we want to prove it's sine 2a. There's one problem with the left-hand side, though. It's not tan 2a. Why not? Nah, it's got to be 1 minus tan squared. So we've got to be doing something else. Okay. Is that what I did? Let's have a look. No, I didn't do that. I decided, I looked at it and went, I'm going to just change everything into sine and coses. The reason I did that, I'm trying to prove sine 2a. The only formula I know for sine 2a is 2 sine a cos a. So I know my answer has to involve sines and coses. So I thought, oh well, let's just change everything to sines and coses. Let's see what happens. All right, let's get rid of those denominators. Multiply top and bottom by cos squared. Oh, that's nice. Look at the bottom of the fraction. Cos squared plus sine squared is 1. And of course, 2 sine a cos a. There's our sine 2a on the top of the fraction. Sine 2a. I mean, it would have still worked, I guess, with sec squared. But at some point, you're still going to have to change to sine and coses. Ta-da! Okay.